In the second part of the first section, I will introduce input attribution method for deep neural network. So this method includes the property of good attribution method. First, I will define what attribution are, and I will introduce relevance score-based method, including layer-wise relevance propagation (LRP), and the gradient-based method, deep lift. And I will demonstrate the equivalence of LRP and the deep lift. And I will discuss how people handle the negative relevance scores. And I will also present a recent method called the relative attributing propagation. This is an example of general setting for attribution method. So when we have cartoon snake, the image come, so we can use black box classifier, which is AI model, and try to predict the label of individual class, including grasshopper, cartoon snake, and green lizard, and so on. And we can use multiple attribution method and then try to find then which area which input pixel contribute the classification of cartoon snake. So that is the goal of attribution method. So when the input where the cartoon snake are highlighted in red, and the other area is either less highlighted or has negative attribution. So we can define those attribution as follows. So given the model, so in n-dimensional input data, so we have x from xn to xn. And we have also c-dimensional one as output, because when the cardinality of c is the number of class or category, so we will define those as s1, x2, sc, x. So we have c of those categories. And the attribution value for each feature for a given class C is written as attribution or relevance score of C input for the class C. So we have n input value. So this is attribution for the class C, n-dimensional data, right? So if we apply this attribution method for the linear regression, so we have two cases. So we have a target y, and we have n-dimensional input x1 to xn. We have a coefficient from w0 to wn plus error. So when yc is the future capital asset, so we have x1 and x2 to investment. Given to investment, the future capital asset will be written as 1.05 times x1 plus 1.50 times x2. So it means that the first investment will have 5% of increase, and second investment has 50% of increase. The influence of the independent variable of the target can be written as, so influence or relevance score or attribution of the first one will be x1, x0.05. For the second one is 1.50. So in fact, the attribution is modeled as like this. So attribution of i's when input will be the partial gradient of output with respect to the xi when we plug in the value x1, x. So influence of the independent variable, this target can be written as, so this, we have relevance score 0.15, 1.50. So when there are two different input, we invest 100,000 for x1 and the 10,000 for x2. Then, so YC is 5% increase of the 100,000 and 50% increase for the 10,000. So we have same amount of the return, edited return, so 5,000. So we can say that in here, so not only for case when we include x1 and also the coefficient 1.05 in here, suppose we may have limitation for the input value x1 and x2. For example, we may not invest more than 10,000 for x2. So in this case, the attribution of x1 compared to the x2 is about like 10 times or 8 times and so on. So we have attribution of input for the first one is 100, 0.5 thousand, and the second one is 115,000. So in this case, we can also compute the gradient of yc output with respect to the xi, and times we can multiply with the input. So we have a two-way of attribution, way to compute attribution. So especially when the data is well normalized, so most of input data has zero mean and one as a standard deviation and so on, then we don't have to multiply, we may not have to multiply the input. But if the individual data may have different input and range and so on, so it would be good to multiply the contribution, the gradient as input as a regard that as a contribution as a relevant score. So to define the property of good attribution method, we need to define some definition. So first one is explanation continuity. On attribution method, satisfy explanation continuity if given a continuous prediction function as Cx, it produces continuous attribution RCx. Because the original prediction function is continuous, it produces continuous attribution RCx. So when there are two nearly identical data points and the model response are nearly identical. So when the prediction is continuous, the attribution is also continuous. Okay. So the second one is in implementation invariance. So when there are two functionally equivalent models, for example, M1 is DNN and 2 is XGBoost. So for any X, the model produces the same output. So suppose that DNN model A, XGBoost model B generates same output for all the input X. Then we can say that an attribution method is implementation invariant when we have two models which produce the same output for the input, given any input X, for the any class C, those attributions that we compute are identical. So because the implementation is identical, so regardless of any algorithm model that you use, so this attribution method recover the same attribution from these two different models for one input at class is given. Another important notion for this input attribution method is sensitivity N. So this notion regards the sum of the attribution for any subset of N feature is equal to the variation of the output as C equals removing the feature. Suppose that we have input variable X, and suppose we have subset variable X S. Then we can have set minus to make X minus X S. So we can say that there is S T score when you apply X, and the score is C when we apply X, then minus X S. So when we have subtraction SCX minus X C X SEM minus XS. So we are computing or comparing the contribution of input without excess, this with excess. Then if we compute the individual contribution of the feature R1C, R2C, and R and C, so on. Then if we sum these individual contribution in excess, the summation of individual contribution that we recover from the attribution method, each summation is equal to the subtraction of the contribution of x minus xcx minus xs. So if it is a case, then we can say that this attribution method satisfies sensitivity n. And when n become the whole set, then this property is the efficiency property in the Shapley value. So if we only get if we have all value and this all value is, so suppose the x bar is a reference value, which can be used for any of x. When we assuming that the x bar is can be recovered from the Shapley value, then we can say that this this is the efficiency property in the Shapley value. So because we didn't define Shapley value formally, I will just say that this is important property, efficiency property. And if it is the case, then we can say that the final contribution of the input can be decomposed into the individual contribution of the attribution that we recover from the attribution method, right? This satisfies always when this is the attribution method satisfies sensitivity capital N, right? This is R1, R, N, X. Is always score. So we say that there is a good attribution method, but in reality, it is very hard to recover these type of theoretical property always. So we may have several heuristic or easy implementation to satisfy this. So like we can have, so as we discussed previously, attribution method in linear model is represented as just getting the coefficient by taking the derivative, partial derivative in terms of output with respect to the individual input, that is a coefficient, linear coefficient. And sometimes we can make multiplication with input, or we can use without multiplication with input. Also, we can say that when we take absolute value of the partial derivative, we can say that there is a sensitivity analysis. And when it is non-linear model, if we can compute the partial derivative for the complex function, then we can say that there is a gradient times input. We compute the gradient and the input. Also, we can take gradient, take partial derivative of f with respect to the xi, where the x point is located, and the times input, grad input, grad input. So goal of many input attribution method is like this. So when there is a garden snake is located in the image, so there are some nodes which are highlighted, And this highlighted node will contribute eventually make garden snake class high value. Then, so we wish to set other value 0 and only care that where the garden snake make garden snake highlighted, and then based on this value, we'll try to back propagate the relevant score and find the location which make garden snake as a garden snake. So one of the methods that make this possible is layer-wise relevance propagation. So or epsilon layer-wise relevance propagation. In here, so we compute the relevance of individual unit I at layer L. So if we have layer L node I, we can compute the relevance. And also, if we have the node J in the layer plus 1, then we can make relation these two as W, I, J, right? And there is a connection from the neuron I to the neuron J. And the value in here is, we can say that the value in here is X, I, L, and value in here is multiplication of value in the node I, and the weight will be the value Z, I, J. So we define Zij as this. Of course, Gij will be summed with other contribution from the other node. And finally, will be taken as a nonlinear function. So then in the LRP, it claimed that so when we wish to compute the relevance attribution of input, we can apply this rule from the last layer to the first layer. Then the computed value will be the gradient times input. So when if unit I is target unit of the interest, so we can say that only if this is the last layer L, then the score will be remained, but the other class will be set to 0. So this is for the garden snake. Garden snake will have its score, and the other class may not have the score value. Then, so this will be propagated back. So with this rule. So this is a relevant score that we can get in the next layer. This is a relevant score that we can compute in the current layer. So this will be the computed for the older node J, which I is connected in the next layer. And the contribution of this will be multiplied by this equation. And the summation of this will be the relevance of the I to the final value for the class C. So in here, the garden snake. So in the input layer, the final attribution is RICX. So if we demonstrate that as a figure, so then you can say that there is a nonlinear function. So this is activation of node J's node in the L plus 1 layer. And this is activation of I's node in the L's layer. And that will be multiplied with Wij and with bias. And that will be treated with nonlinear function. So in here, it's Aij, Aj, and this is Wij, right? So this multiplication will go to Zij. So when we omit the bias term and the epsilon term, and this is normalization of the contribution of the output in the next layer. So how much the ice node in the previous layer contribute this JS node in the next layer by considering all the possible Z connected this J and the portion how much I contribute to J when we consider all the possible I prime is multiply with the relevant score of J, and I will collect all of those contributions based on all the possible node which is connected in the next layer. So if we have a ladybug image, then after that, the location where the ladybug is will be highlighted. So this chain rule, a single path is produced, the partial derivative, and either this is nonlinear, linear model, and so on. So if we have two units in the unit I and j in the subsequent layer, then so xi and xj, then so this is connected by w j I, and so this will eventually have f g j. Then if we take a derivative, because this is xj, right? And we can say that, so if we take derivative of xi in terms of xj, and we will say f prime dj times wij, wji. So we can compute this gradient partial derivative when even if actually C is located in the last layer in the class and Xi is located in the previous layer and so on. What we can do is we can consider all the paths that whenever we take a partial derivative in here, so this will incur the recursively the partial derivative of this node and like a gradient times, and we will multiply the weight in here. So any path in here will give us the gradient of the node and or the multiplication of weight for all the possible paths. So we can define gradient of f prime, which is a nonlinear function, as g. Then so we can apply this rule for many network which has fully connected one and the convolutional one and the recurrent layer without multiplicative unit or pooling operation. So this is applicable for the fully connected convolution recurrent layer. So we may need to treat for the pooling operation, so on. So NLP is equivalent to the feature-wise product of input and the modified partial derivative of this final output make partial gradient with xi with respect to g when we assuming that g is GLRP is this form, and we assuming that that can be represented as f prime z. We approximate this. So when we use value function, hyperbolic tangent, and because f is the activation function, and so if we take any of gradient in here, so when f is the value, then we can say that the fg value, this is g, fz, fz divided by z will give us the gradient of the value case. That is the same for the hyperbolic tangent case. So in a sense that if we say the GLRPZ is this equal to F prime Z for ReLU and hyperbolic tangent. It is not the case for the sigmoid function and the subsurplus function. So we can prove this by induction. So by definition, the epsilon and NRP relevance of the target neuron C on the top layer can be represented as recovering the original function. So this is the activation function, nonlinear function. So we can put, so the summation to the C class is, so we are taking the value from J to C, and so we are like, this is a weight from the last layer, from the previous layer, and we are multiplying all the possible value in the previous layer, xj, and the bias. So by this definition, so we just actually rewrite with activation function. So we can apply this in the last layer. Suppose we wish to get the relevance score for the L-1 layer. So we can put this, our previous equation in here with LRP rule. So LRP rule is simply the multiplication of this with Z and with the possible J prime in the previous layer. So that is a multiplication of J prime to C and with the bias. And this is by definition of the final value. And so by definition of GLRP, so you can focus on that. This part is, if we say Z, is identical with the equation part in Z. If you remember that, FZ divided by Z is G LRP G, then we can rewrite the term as this. And so by the definition of the this gradient of G with respect to the final outcome in the input here, written in here, so the gradient term can be represented as all the possible paths. In this case, all the possible path is just a single path, right? And if we compute the GLRP here, right? And we can multiply the weight WP from J to C, right? And this will become the equation that we define here, and the multiply with the input in the previous layer. So this is a gradient times the gradient, which is with respect to the J's node in the L-1 layer times input. So that is a relevance score that we recover. So of course, this is a linear model, very close to the linear model. It's not really unexpected. So we can apply this to the previous layer. So assuming that the induction step hold for the else layer, and the relevance score can be represented as gradient that we compute whether GLRP hold, and then gradient of SCX partial derivative over XCX with respect to ith node in the else layer times input. Then, so we can say that we can also apply the LRP rule. So LRP rule. So this is LRP rule in the layer from L-1 layer to S layer. Then we apply the definition of RIL as shown in here. So this is the LRP rule, and we can focus on that. So this is XL and WIJ, and yeah. So XIL is coming from here, right? And this part go to the second term, right? And what we can say is, so by the definition of XIL, else node in the ith node in the else layer, so there is a summation of all the possible value from J in the previous layer, J prime, to the I. So in that sense, this is all again F, if we set that as Z divided by Z. Then that is also again G, LRP, and XIL, right? Of course, this XIL is the 1Z that we represent. G, LRP, Z, right? In that sense, we can also rewrite this equation as GLRP times Wij. So in a sense that, so we can say this is a J's node and these are I's node. So as you see here, so we can make a multiplication of all the possible G and we also have the partial derivative in here for individual I. Suppose we have this is 2 but I, and we can make a multiplication with all the possible paths are computed as a gradient, partial derivative G, LRP, SC, X with respect to X, I, L. So this is already computed. So here we now compute GLRP, XIL, and we multiply these Wij, and then we'll set. So we need to summation all the possible paths from first to the second one to the last path. And this is a summation of all the possible paths. Then this is coming out. Then this will be the gradient of final output with respect to the J's node in the previous layer, n-1 layer times input. So we can hold that. So this LRP will satisfy gradient times input when fx, fz divided by z is a gradient. In many cases, as we've seen here, so sigmoid function and other function and this gradient does not hold. So what we need to do is we need to have baseline input. When we have a baseline input, then we take baseline input out from the final output. So this is input and the SC is a contribution final classification output score for the X. And we subtract the baseline input and in the final layer and also in the previous layer in the each layer, and we take baseline value for Z and take subtract to make this value correct in terms of finding the gradient. So if it is a case, then we can say that if epsilon LRP is equivalent to gradient times input, if only value are used as nonlinearity. That is what we have shown. And also we can show the deep lift computed with the zero baseline if applied to the network with no additive bias because zero baseline with the nonlinearity f such that f0 is 0, then we can say that epsilon LRP is equivalent to the deep lift 2. Like as you said in ReLU and the hyperbolic tangent. Of course, deep lift will hold for this property. So deep lift may not be the heuristic. It's not heuristic when we use different functions, sigmoid function and the subtoplus function. So there is a improvement for the deep lift compared to the epsilon LRP. And also, but like this computing the baseline may not be uh, good enough. So what we can do is, so we can do the integrated gradient. So because actually LRP and the dim lift is just finding the base point and finding x and taking those subtraction, then we can approximate the result gradient. So what we can say is, so we can integrate the gradient as shown here. So this is x bar base point, and if we say x is what we wish to get, and so we can set based on the alpha, this is x tilde, and we integrate those partial derivative of x tilde, so partial derivative of this SC from x bar to the x through x tilde, and integrate all those value out from 0 to 1 and alpha and multiply with the input. So that is what we called uh, integrated gradient. So integrated gradient is accurate even though we need to sacrifice the computational efficiency, and it satisfies theoretical sensitivity and property, which we discussed in the shuffle value. So sum up, so we can say that there is sensitivity analysis taking the absolute value in terms of this gradient and multiply with input, and we can compute this gradient recursively with this assumption. So this assumption can be lifted by finding the base point. So this is more general case. In the also integrate gradient is taking the integration of this gradient, then this will satisfy sensitivity and property, even though it's very hard to compute in practice. So if you apply this attribution method for this cartoon snake scenario, then we can take this is a gradient times input, and this is integrated gradient, and this is deep lift, and this is epsilon LRP. So you can see that epsilon LRP and the gradient input are similar, and the integrated gradient highlight more the area where the cartoon snake is. There are various applications of this method, and as an example is autonomous driving, autonomous car. So this is a pylon architecture designed by NVIDIA, and this method, so when the RGB input come, and the pylon net will decide, so out of 10 angle, which angle this we should go. And so this is, so whenever the decision is made by the PiloNet, the input attribution method find the location. So when the steering wheel turning left, then the input attribution method find the car and the road, which is tilt to the left. And when PiloNet decide to go straight, and this area is this area contribute to find to go straight. And when the pilot decide to go turning right, and the area contribute to find is this area. Right, so this is reasonable result. And also when, so as we discussed, the method is a little bit complicated, and the one method we can consider is perturbation method. So the thing is, so this is original image, and this is image that we apply. So we put some hole with gray box, either base value, minimum value, or average value, and so on. So we can find the final output, how much cartoon snake will be predicted. And we also predict how much cartoon snake is predicted when this part is occluded. And then, so the difference of this score will be the score for the perturbation method that compute the attribution. So we have occluded the where the cartoon snake located, then the drop of this cartoon snake class will be um, decreased much. So in that sense, we have occlusion of for 1 pixel or 5 by 5 area and 10 by 10 area or 15 by 15 area, and we can say that we can see that. So if we feel the only pixel that the wrong area are detected, but if we go to 10 by 10, the area is close to cartoon snake. If we go to the 15 by 15, then this area is close to the where the cartoon snake is. So these are methods that is related to our method, what we discussed, and the gradient input and the layer-wise relevance propagation, integrated gradient, and deep lift, and so on. So there are, and the simple occlusion, and there are other methods for this. So one of the issue with this relevance propagation method are, so when there is a pass from the input to the output, in many cases, even if we use rel a lot, so some layer does not have um, ReLU nonlinearity, meaning that some negative value will directly go through the computation of the final output, especially in the last layer. People may not put nonlinearity value much. And any positive or negative value will go through the final outcome, right? And then, so when we compute the propagation in the final output, relevance score in the final output, then the some node will have positive value, but the other node will also have a negative value. So we can take positive value and negative value and then relevance propagation, right? But in this case, so that is actually like empirically observed much, and the positive attribution and the negative attribution concentrating the location where the object is. So that is the issue. So we say that we wish to have that the positive contribution is in the object and the negative contribution should be located in the external area. So to solve this issue, there are many methods are proposed. So this is positive forward pass, and this is plus, plus, minus. And when we use ReLU, then this minus so like suppress, then the path like a value go through the node. And when the gradient comes, then this value, because this value in the gradient method, because this value is does not contribute to make the final output, especially when the output is binary classification, and the value does not go through, the relevance score does not go through this activation node. But somehow, so if we don't have binary classification and the other negative value come, so it is not sometimes good. So the CompNet try to say that, so let's try to not to pass, like we can allow the relevance which are positive even if we was not contribute to the output, but does not propagate when the relevance score is negative. Right? And also guided backprop, remember the previously negative activation and also negative relevance score. So in both cases, the relevance score does not propagate to the input. So then only this path will be used to compute the relevance score. So recently there are other methods are proposed called relative attribute propagation, which is written with my colleague. And the heuristic on this idea are simple. So because as we seen here, so most of negative and positive contribution are actually located concentrating on the object. So we can say that instead of just sign as a good indicator, but just take absolute value or indicator. So even if negative value will be regarded as enough good contribution relevance. So we'll just take the absolute in the last layer where the nonlinear activation does not apply. And also, this model has a unique property called uniform shifting. As we do the batch normalization in the training procedure, we also apply the uniform shifting called like a batch normalization when to normalize the signal into the positive and negative one. So when we have mostly positive signal, except with some negative one. So we'll try to take the little negative one is strongly negative and less positive one is negative. And also very strong positive one become less stronger. So this is like inverse procedure as we do in the batch normalization. Relevance score we normalize in this way. So surprisingly, so if you apply this method, of course, integrated gradient is actually the close to what deep neural network methods have seen because it satisfies sensitivity and property. So especially when we see the Dalmatian, so we can see that the integrate and see this part, the characteristic, of course, so the white dog is not really good. But the eye and also the mouse part will be highlighted and so on. So minibus cases too. So if you compare with other method, then the other method may suffer from the actually finding the crucial property of those methods. But you can also see that the strong negative one in the integrated gradient also concentrating on the object part, right? But if you apply this heuristic for this relevance propagation and RAP take clearly where the relevance location have. And the third phase, suppress any activation which is not stronger but which is outside of the object. So in that sense, it is close to the human interpretation or human-friendly interpretation as semantic segmentation. So if we compare this into the two cases, outside-inside ratio, whether how much the classified sample is get inside of the box, which is Coco data set, or out of like a versus out of no, out of the location. Then so we can see that so the out of inside ratio is very small in the RAP case in the compared to the other case. And also if we take this as compared with the semantic segmentation mask that's human made, then we can say the RAP is stronger than the other method. Strongly correlated in terms of mean intersection of union. And when we perturb the negative attribution, so suppose this is object, and if we perturb the part which is outside of the object, which is negative, and we can see that this in VGG and the resonance 50 and this RAP method least perturbed by the perturbation, the location where the object like outside of the object. So this is a conclusion of the input attribution method. So the input attribution method compute the contribution of input feature through the output of a differentiable but complex function. And under some condition like ReLU and hyperbolic tangent, one can compute the gradient of dim numerator well recursively, which is exact to the gradient. And some recent methods like RAP can clarify the silence object with some heuristic as we discussed. Thanks for listening.